Okay, with this set of examples, we're going to look at how to calculate the analysis of variance test statistic. The example we're going to look at is the following. Suppose that some investigators think that the concentration of a particular antigen in supernatant fluids could be related to the onset of meningitis in infants. The accompanying data is typical of that given in plots appearing in the paper. Type-specific capsular antigen is associated with virulence in late-onset Group B streptococcal type 3 disease. And it has three different categories: asymptomatic infants, infants with late-onset sepsis, and infants with late-onset meningitis. And it gives me 8 measurements for each of those. And again, this is a measurement in concentration of a particular antigen. And what I want to know is if there's a difference between these two. Our null hypothesis is that the average concentration is no difference between the three. The alternative is that at least 2 of these are different. In order for us to calculate the F statistic, we need to know the between variance and the within variance. That relies on us having some information about the averages and the standard deviations for each set of numbers. So we're going to say that we're going to let a subscript of A be asymptotic and X with a little s as a subscript will be for those having sepsis. And we'll use a subscript of an M for meningitis. If we take the set of numbers and we plug it into a calculational formula, we can see that the average for X sub A is 1.115. For B is for sepsis is 1.553. And for meningitis is 1.736. And the standard deviation is 0.106, excuse me, the variance, and 0.103 and 0.324. So in Excel, I just went ahead and had to do the average of each of these numbers, and this is the standard deviation of those numbers. And what we want now, then, is to calculate the F statistic, which is the between variance divided by the within variance. See if I can write that so it's actually a little more readable. There we go. Now, the within variance is the average of the sample variances. So in this case, it's going to be 0.106 plus 0.103 plus 0.324 divided by 3, which turns out is Hold on. .178. Okay. Now, so we took the average of these threes. So the average here gives S sub W squared. To get S sub B squared, I have to have to get S sub B squared, that's N times S sub X bar squared. And S sub X bar squared is the variance of the sample averages. What I mean by that is we have X sub A bar, so the asymptotic is 1.115. The X sub S bar, those that had sepsis, was 1.553. And those with meningitis was 1.736. The overall average, using all of the data points that we had, is actually 1.468. So to get S sub X bar squared, I'm going to take each of the sample averages and I'm going to subtract off the overall average and square it. And then I'm going to divide all of that by the number of categories minus 1, which in this case there are 3 categories, so I'll divide by 3 minus 1, or 2. And that will give me a value of 0.10185, 0.10185. So then S sub B squared is equal to the number of observations, which is 8, in number of observations in each row, times that 0.10185, which gives me then 0.815 as my between variance. So now the F statistic is S sub B squared over S sub W squared, which in this case is 0.815 over 0.178, which turns out to be 4.59. So that's our test statistic. And I can get that by doing calculations by hand as well. Again, in Excel, I took the average of each row, which gave me these values. I took the standard deviation of each row, which gave me those values. The average of those 3 was the 0.178. The overall average of all of these values was 1.468. So I then took each row average and subtracted off the overall average. So if I take 1.115 minus 1.468, that gives me minus 0.353. And I'll do that for each one of them. I then squared all of those values. So these represent the sample averages minus the overall average, quantity squared. I add all those up. I then divided by the number of categories minus 1, which would have divided that by 2. To get S sub b squared, I then multiply that value times the number of observations in each row, which was 8. And then my test statistic is taking this 0.81483 and divide it by the 0.178, and it gives me 4.5882. If we wanted to do this in StatCrunch, we can pull up StatCrunch here. And I can copy my data sets over. And in StatCrunch, it does need to be in columns. So this is asymptomatic. And this would be sepsis. And this would be meningitis. Okay, I can go in and I can do stat analysis of variance. One way, I'm going to select my 3 columns. I am then going to hit compute, and notice it gives me my averages that I used in the previous example. It also gives me the standard deviations. If I square those standard deviations, I get the variances that I had in the calculations I used. You'll see mean square columns is 0.8148. This corresponds to the between variance. It's the mean square error, or the mean squares difference between the columns. So between columns. And the mean square error is the variability within a column. So this number represents S sub b squared. This number represents S sub w squared. If I divide this one by that one, I get my F statistic, which is exactly what we had. And it will give me a p-value. Again, we said that we won't make you use an F table here. Well, if we want the p-value, we'll always go through the statistical package process. And this would give me a value of 0.022, which would tell me that I have a very low likelihood that these have the same average. So if I wanted to know which ones had a different average, we can do what's called the Tukey comparison test. And I can go through and do the same process I just did, but then I'm going to have it compute the Tukey test, what that does is it, instead of doing pairwise comparison, it does the comparisons in such a way that the overall error rate is our level of alpha 5%. Notice that by having the Tukey results, it does the same thing as it did before. It gives me an analysis of variance table, but then it shows me some other information. And the way that it's worded is basically what happens is it constructs a confidence interval between, or for the difference of one variable from another. So in this case, if I take the asymptotic or asymptomatic individuals and I looked at the average difference from them and those with sepsis, and I create a confidence interval, it gives me a lower bound and an upper bound for that confidence interval. If that confidence interval contains 0, then we do not have enough evidence to suggest that the averages are different. So in this case, because 0 lies in this interval, we do not have enough evidence to say that those that were asymptomatic are different than those that had sepsis. However, if we look at the confidence interval for meningitis minus asymptomatic, we see this does not contain 0. Because this does not contain 0, there is no overlap between these two, and we can conclude that there is a difference in the average concentration for those with meningitis as opposed to those with that are asymptomatic. And for sepsis subtracted from those with meningitis, we see that this one does contain 0. So we do not have enough evidence to say that those with meningitis are any different than those with sepsis. Okay. So for this example, we had that asymptomatic was not the same thing as those with meningitis, but we had no proof that those that were asymptomatic is different than those with sepsis. And those that had sepsis, we had no proof that they were different than the meningitis. There was enough evidence to say that these two things were clearly not the same average. However, both those that were asymptomatic and those that were sepsis had some overlap, so I could not tell the difference between those two. On the other end, we also had an overlap between those with sepsis and those with meningitis, so that we weren't able to tell a difference there. How could that possibly happen? Well, we can think about it as we have a confidence interval for asymptomatic. We have some overlap with sepsis. And then over here, we've got another overlap with meningitis. So both sepsis can overlap both of those, but these can still be far apart from each other. Now, the type of question that I would normally ask on something like this in an exam would be, I would give you summary information where I would give you sample averages and sample variances and would ask for you and the overall average. and then ask you to calculate the test statistic. So I would ask you to calculate the between variance or the within variance. I may ask you to calculate S sub x bar squared from the information. I could also, if I wanted to make it a little easier, I could give you a problem where I gave you S sub x bar squared, so that all you had to do was know the relationship between S sub x bar squared and S sub b squared to simplify those calculations. I could ask you to calculate the F test statistic then from those two values. And it's possible that I could ask for you to interpret the information that came out of a Tukey's comparison. Again, remember, if the confidence interval that's created from Tukey's method contains 0, I cannot say there is a difference between the two things that are being compared. If the confidence interval does not contain 0, we can conclude that there is a difference between those two items. And notice that each one of those has a p-value as the likelihood that they are different from each other. Well, that concludes our discussion of examples for the F test statistic. You'll get some more work with this in doing your lab, where I will have you put some things in StatCrunch and calculate some summary information and go through the process of calculating the F test statistic and then verifying the result with the StatCrunch to back you up or to give you help. So that concludes our example portion for analysis of variance.